Hello students, my name is Shashank Shekhar. So we have started enthalpy of reaction. Okay, so in which we have studied various type of enthalpy of reaction. So we will study some of them more, some more of them. So if I talk about those, so we will talk about enthalpy of combustion. We will talk about enthalpy of atomization, bond enthalpy, okay, and enthalpy of solution and dilution. So these are some enthalpies, some more enthalpies that we will study today. Yesterday we learned about this enthalpy of formation. So it is very important. Now, what is important in this enthalpy concept is that you should remember the actual thing. Okay, what is the actual definition? You should be aware about that. Then and then only you will be able to answer the question in case of thermochemistry, right? So this is very very important. So suppose I am saying that what is enthalpy of formation, then you should know that its definition. That okay, it is the formation from its constituent element in the standard state and taken the so if you're talking about standard enthalpy of formation, then the conditions should be also standard. So these are the things that you should focus upon, right? Similarly, we talked about the enthalpy of transformation. So what is different about a standard enthalpy of transformation is that you don't have to specify the temperature. Okay, it depends upon the enthalpy of it depends upon the boiling point or the evaporation or the phase transition that you're talking about. Okay, so it does not take in account into temperature. So that thing is important, that what are the specificities of different combustion that should be considered. So let us move with this thing in your mind. Let us move to the standard enthalpy of combustion. So first of all, if I talk about combustion, so combustion is a exothermic reaction. So it is very obvious. Okay, so it is exothermic. That thing is very obvious. Just think of it in a way that if you burn a paper, right? If you burn a paper, you just provide a small spark of say fire, and it starts to burn. And in that process of burning, it gives a lot of heat, and it is very much greater than the heat that you have provided initially. So that makes it very confirm that okay, your combustion reaction is a exothermic reaction. Now, since it is an exothermic reaction, it means it release heat. Okay, and that heat can be used in very various things, because heat is a form of energy, of course, and energy is very important in our modern life. So whether we talk about industry, rocketry, or any other walks of life, we need energy there to process the life, or you can say to make life more stationary. Okay. So let us now move to the definition. So you should be very conscious about each and every term of definition that I will speak. So, what is standard enthalpy of combustion? So, it is basically the enthalpy change per mole of a substance when it undergoes combustion, and all the reactants and products being in their standard state at the specified temperature. What is the meaning of this? First of all, the first very important point, that if you are seeing a thermochemical equation, then the number of moles that are involved in combustion, or the thing about which you are talking about which you are going to combust, it should be present as 1 mole. Or if it is not present at 1 mole, you are suppose calculating it for x mole, then divide the value of the enthalpy by x, so that you can get it for each mole. Okay, clear? Next thing is important is that the reactants and products must be in their standard states. Okay, so if you know, if taking oxygen, it should be in gaseous state and at the given standard conditions. If you're talking about that compound whose combustion you are going to do, it should be also in the standard state, and that also at a specified temperature. So, for example, if I talk about the other say uses of this combustion, so simple it is. You can talk about the cylinders. In cylinders, we have butane. So that thing is burnt, and during that combustion, 2658 kilojoule of energy is released. For 1 mole of butane, 2658 kilojoule of energy is released, and that is used for cooking. Clear? So, what is the standard enthalpy of combustion for methane? It is 2685 kilojoule. Now, let us try to understand with the help of some examples. So let us take a thermochemical reaction for that. So here we are taking the butane. So for butane, we need 13/2 of O2. So that is very important, that your equation should be always balanced. So see, it is balanced here. 4 carbons on the left side, 4 carbons on the right side. 10 hydrogens on the left side, 10 hydrogens on the right hand side, 5 to the 10. Okay. And talking about oxygen, so there are 13 oxygen moles on the left hand side. Similarly, on the right hand side, 4 to the 8 plus 5. Okay, so here also 13 oxygens are there. Clear? So if you think about this process, so in this process, the enthalpy of combustion is minus 2658 kilojoule per mole. We have told this. So now you will ask that you are telling it a minus. Here it is not written as minus because the system itself, the statement itself verifies that this is released heat. Okay, so it is already written that it is the released heat. But here it is a numerical value. We have no statement to support it. So we write a negative value to specify that your heat is released in this case. Clear? Okay. Now, similarly, if I talk about the combustion of glucose, which occurs in your body to provide you, say, heat energy for your daily work, so that is having a value of 2802.0 kilojoule per mole of heat. Okay, which for which the overall reaction is this. Okay, so this is the overall reaction. Here also, all these atoms are balanced. If you see, now, in this case, more amount of energy is released as compared to butane. Now you can think of the amount of energy that you consume daily on a daily basis. So that is even greater than the butane. Means I'm not saying it is greater, but it is even greater than the heat released on combustion of 1 mole of butane. Clear? Okay. So this is about the standard enthalpy of combustion. Okay. Now we'll solve a problem related to this. So I will first. This has two ways to solve. There are two ways to solve this question. First way is written here. Second way I will dictate you. Okay, so if you want, you can do it in that way also. Second one is more easier to do. So the first way you will see here. Okay, the first way we'll see here. So first of all, let us interpret the question. What the question is saying. The question is saying that we are given 1 mole of benzene and we are combusting it. Okay, we are combusting it at 298 Kelvin and 1 atm pressure, right? So for that, we take 1 mole of benzene, we combust it, and after combustion, the CO2 and H2 will be produced because it is a organic molecule or simple hydrocarbon, so it will always produce CO2 and H2O. And in this reaction, 3267.0 kilojoule of energy is released. Okay, so this is the enthalpy of combustion. Second thing is that is given is that calculate the standard enthalpy of formation for benzene. Okay, if the standard enthalpy of formation of CO2 and H2O is given as minus 393.5 and 285.83 kilojoule per mole, because it means that standard enthalpy of formation for both of this compound is given. So what we have to find actually, we have to find the enthalpy of formation of benzene. So what is the way to form benzene? So there are two atoms there, carbon and hydrogen. So we'll add both of them in the standard state. So carbon is graphite in its standard state and hydrogen is H2, simply H2 gas in its standard state. We will add both of this to get C6H6. So this is the equation related to formation of standard formation of reaction. Now, if I talk about the combustion, so with combustion reaction follows this equation. Okay, so it should be very clear because we are burning benzene in presence of oxygen, and it will of course give you what? It will give you carbon dioxide and water. Clear? Now if you balance this equation, here 6 will be coming, here 3 will be coming, here 15/2 will be coming. Now what are the data that are already given? So this data is given. First of all, the standard enthalpy of formation of say CO2 is given, right? So this thing is given. It is given as minus 393.5. So we can write the equation in this way, that C graphite plus oxygen will give you CO2, right? Similarly, enthalpy formation of H2O is given. Therefore, we can write that, okay, how it will be formed? It will be formed from their atoms in their standard state. So H2 will be in the gaseous way to be in the standard state. Similarly, O2 gases will be the standard state. So we have to form 1 mole of it. Okay, so it should be in your mind that since we are talking about standard enthalpy of formation, so 1 mole of it should be formed. So that would give you delta H formation of this H2O as minus 285.83 kilojoule per mole. It is given. Now this equation, these two equations we have, and their thermochemical along with their values Okay, this equation we have along with their values. Now we have to do an algebraic, you can say, contribution to add or to subtract or to multiply to get the final equation that we need. So here one graphite is there, but we need 6 graphite on the left hand side. So first of all, what we will do, we will multiply this equation by 6. So this is the first thing. Second thing, we need 3 H2s, okay, but here only one H2 is present. So we will multiply this whole equation by 3. This is the second thing, and we need both of them on the reactant side. So we'll add both both of this equation by multiplying upper one by 6 and lower one by 3. Okay, now we will add this. So here same thing is done, multiplying by 3 by 6 and 4 by 3, and then adding both of them. Okay, so you will get this equation. Now, if you just compare it with the equation that we are in search of, then you will see that, okay, we have 6 graphite, 3 H2 and C6H6. But C6H6 is not here. Okay, C6H6 is not here. We have 15 by 2O2, we have all of this, but 16H6 is not there. So we need C6H6. So if you see this equation here, combustion equation, then you will find that C6H6 is there, but it is on the left hand side. We need it on the right hand side. See, it is on the right hand side. So we'll reverse this equation, and this will reverse the sign. So here, this thing is reversed, and this gives us positive 3267. Okay, so this should be positive here. So this will give you positive 3267 kilojoule per mole. Now add this equation 5 and 6. This will give you your final equation. 6C plus 3H2 gives us C6H6, and this is your answer. Okay, so here it will be positive, so therefore we need a difference here. Next thing that we will study is enthalpy of atomization. So this, let's listen to this again. Definition is very important. So what does this definition says is that what you have to do if you are taking an element or a compound, then you have to convert those into single atoms, and those atoms should be in the gaseous state. See here, we have taken H2 gaseous and converted it into gaseous atoms, okay, 2 hydrogen gaseous atom, and for that the enthalpy of atomization, it comes out to be 435.0 kilojoule per mole. Now you can see that hydrogen atom is formed by HH bonds in dihydrogen. So this is also called as bond enthalpy, because it is the amount of energy that is required to break the bond between H and H. Okay, before that we are talking about enthalpy of atomization. So what are we doing? We are converting this into atoms that are in the gaseous state. Okay, so we can take more examples. Suppose we are given CH4 molecule. So this is a diatomic molecule. So what you will do, you will, if you just want the enthalpy of atomization, then again you will convert this into carbon. Okay, carbon, single carbon, that is in the gaseous phase, and 4 hydrogen atoms that are again in the gaseous phase. So in this case, the enthalpy of atomization is 1665 kilojoule per mole. Clear? One more example is given. If you are taking sodium solid and are converting into sodium gaseous, then you are getting what? Atoms that is in the gaseous state. So it is also enthalpy of atomization, and its value is 108.4. Now here, this conversion is what? It is simply sublimation. If you talk about this equation, then you are simply subliminating Na solid, sodium solid, into sodium gaseous. So it is also called as enthalpy of sublimation. Clear? Okay. Now next, it is bond enthalpy. Okay. Next it is bond enthalpy. So what is bond enthalpy? So bond enthalpy is basically breaking bond. It is the amount of energy that is required to break a bond, or the amount of energy that is required to make a bond. Clear? So in both these processes, either energy is released or energy is taken. Now it is possible to relate heat of reaction to changes in energy associated with breaking and making a bond. Now there are two types of bond enthalpies. Okay, there are two types of bond enthalpy. First is bond dissociation enthalpy. Okay, first is bond dissociation enthalpy, and second is mean bond enthalpy. So we'll talk about it with the help of an example which is given here. So we have said already this, we have seen already this equation. So here what we are doing, here we are atomizing this H2 gas into 2 atoms of hydrogen. right? So what are we doing? We are doing atomization. At the same time, we are breaking the bond between hydrogen and hydrogen. And in this process, the enthalpy change for reaction is 435.0 kilojoule per mole. Now, the enthalpy change involved in this process of dissociation is the enthalpy change that is required to break the hydrogen-hydrogen bond, okay, and to form products in the gas phase. Clear? Okay. So this is the same as the enthalpy of atomization, and this thing is true for all diatomic molecules. Means for all diatomic molecules, the enthalpy of atomization is equals to the bond enthalpy. So this is very important point. It can be asked in terms of statement. Okay. So again, I am repeating. In case of homodiatomic molecule, say hydrogen, or say we are talking about Cl2 chlorine. Okay. So in all these cases, the enthalpy of atomization is the bond enthalpy. Similarly, here we have more examples. So here we can also call this as say bond enthalpy or enthalpy of atomization, in which we are converting Cl2 gases into two atoms of chlorine, right? Next is oxygen is getting converted into two atoms of oxygen, right? So in this case, the enthalpy of bond enthalpy or enthalpy of atomization is 242 kilojoule per mole, and this is 428 kilojoule per mole. Now, what about this polyatomic molecule? So in this case, means in the diatomic case, we have only two atoms and one bond. So whatever answer comes, that is the bond dissociation enthalpy for which we are looking for. But in case of CH4 molecule, a molecule like CH4, this is not the case. It is a polyatomic molecule. There are more than one bonds between C and H. So therefore, what we do? So first of all, we start cleavaging each and every hydrogen. Okay. So if you do this cleavage, okay, you will get this value as 165 kilojoule per mole. So suppose these are the steps. So first CH4 to CH3 and H, so say 427, then again 439, 452, 347. So in this way, we are taking away the hydrogens from here, or breaking one bond between carbon and hydrogen. Clear? Okay. Now, of course, the enthalpy will be high for, say, if you are just breaking more and more hydrogen bond, the successive energy is increasing, irrational of this context. Okay, so this is decreasing from here to here. Other than this, all are increasing. Now there are multiple bond enthalpies here. More than one bond enthalpies are available. See, right? You can easily see it. So what you will do is you will take the average. So we'll simply add all of this and take the average of that, or this is called as, in this case, we will call it what? We'll call this as bond enthalpy. So what we are taking instead of bond enthalpy, we are taking mean bond enthalpy. Clear? So this is the same thing mentioned. So 1 by 4 of delta H atomization, it is 416 kilojoule per mole. Now we find that mean CH bond enthalpy of methane is 416. We have seen that. Now it has been found that CH bond enthalpy differs slightly to compounds as in CH3, CH2Cl or CH3NO2. So using Hess's law, bond enthalpy can be calculated. So we'll see what is Hess's law. So bond enthalpy value of some single and multiple bonds are given in table, which we'll see in the next slide. Now the reaction enthalpy are very, very important, and this arise from the changes that accompany the breaking of old bonds and making of new bonds. We can predict enthalpy of reaction in gas phase if we know different bond enthalpies. Clear? Now, why are this bond enthalpies important? So we have seen that we can write the enthalpy of reaction in terms of enthalpy of formation. So similarly, we can also write them in terms of bond enthalpies. So bond enthalpy, summation of bond enthalpy of reactants minus summation of bond enthalpy of products. So this will give you what? This will give you enthalpy of reaction. Now the net enthalpy change of reaction is the amount that is required to break all the bond and the reactant molecule minus the amount of energy required to break all the bond in the product molecule. So it is basically this, right? So what we are doing is we are breaking all the bond on the reactant side and we are breaking all the bond on the product side. And the energy difference between these two is what? It is called as enthalpy of bond enthalpy or bond. Okay, this is called as bond enthalpy. Clear? Now this is an approximate relationship and it is valid, okay, for some all substances, almost all substances that you will see. So here is a bond dissociation enthalpy for different molecule. So Hi, HBr, HCl, HP. So this is our bond enthalpy. For different combinations, we have different values. So what you have to combine in this way? Suppose you're combining these two, then you will get 297. If you combine these two, then you will get 243. So next important thing, that bond enthalpy value increases with increase in bond order. So nitrogen have initially suppose two bonds. So that will give a value of 418. Now nitrogen triple bond N has a value of 946. Now again carbon and nitrogen has a bond enthalpy of 615 and carbon and nitrogen with a say 3 bond order has a bond enthalpy is a bond dissociation energy of 891. Clear? For oxygen double bond oxygen it is 498 Kelvin. Now next we'll talk about lattice enthalpy. Okay, next we'll talk about lattice enthalpy. So what is lattice enthalpy? So it is basically the amount of enthalpy change when 1 mole of a solid it converted into its ions. See, so the lattice enthalpy is the enthalpy change when occur when 1 mole of this ionic compound. So this is very important that 1 mole of the ionic compound should dissociate into ions and not more than one. So for suppose NaCl, this value is 788 kilojoule per mole. Now we'll try it and try this Bonds-Haber cycle, so which is very useful for the thermochemical equation. You already used it, but still I will try it one more time. Now I have said you earlier that I will solve one question also through two methods. So second method I will just demonstrate here it right now. Okay, this was the question. So if you want, you can write this say combustion reaction enthalpy in terms of standard summation of standard enthalpy of formation of the reactant product minus sum of standard enthalpy of reactant. Okay, so we'll subtract both of this and we'll get a value. Okay, but one thing is to notice that if you're talking about CO2 standard enthalpy of formation, and if you're doing it for the equation that is combustion of benzene, then it should come along with 6, because if you balance the equation, you will get 6 CO2. And here the value is given for 1 mole of CO2. So multiply it by 6 and you multiply it by 3 for H2. Then reactant minus product. In the product side, we have CO2 and H2. In the reactant side, we have C6H6. So we have to calculate. For O2, it is already 0. You can calculate all this, put this values here, subtract product minus reactant. You will get your same value as this solution. Okay. So we have talked about lattice energy. So we'll just try to do it with the help of Born-Haber cycle, which is very important from exam point of view. So first question is what? So this diagram is what? So here we are talking about the lattice enthalpy of NaCl. Okay, we are talking about the lattice enthalpy of NaCl. So here is a table for you. You can say it is a chart for you that can help you to do so. So first we have what? Suppose we are starting it from here. Okay, we are starting it from here and we want to make NaCl. So we will take 1 mole of sodium and half mole of Cl2. Now in the next step, we will do the sublimation, means each of this will be converted into gaseous phase. So sodium is converted into sodium gaseous phase, right? Next is what? Next what you will do? You have the metal ion, just combine them all, or this will give you NaCl. What is the other method that we have? So the other method is that, suppose first what we do, we subliminate this sodium to get sodium solid. Okay, we sublimate it to get it sodium solid. Then what we can we do? Then in the next step, we will do the sublimation of this solid into gaseous. So del H sublimation of this. Next is what? Next is delta H ionization. So what are we doing? We are converting this, or you can say breaking the bond between the two Cls. Okay, so that is written as bond. Okay, this is written as bond ionization enthalpy. So here we are converting. Okay, here we are converting what? Bond enthalpy. Okay, we are breaking this bond. So 1 mole of Cl, but here it is at half mole of Cl. You will multiply the value by half. Okay, clear? So this is our thing. Now next, one more important thing is that if we just treat this sodium with H plus, then it will give you sodium plus. Okay. The next step, what will happen? Next step, what we'll do? We can do it in the other way also, as I said. So we are going through that state. So we got Na plus and Cl gas. Next, we will do the electron gain enthalpy reaction, in which the Cl will gain electron and become Cl minus. So Na plus Cl minus. So this is converted into NaCl, and this is called as lattice anhydride. Clear? Is this clear for you? Okay. Now next. Okay. So this is our thing. So in this way, we can calculate it in two ways. Now let us just write these things in word. Okay. So first of all, we will convert sodium solid into sodium gaseous. So this is called delta H sublimation. In the next step, we will just abstract one electron from sodium. That will give you sodium plus. So you have got your sodium plus ion. Next thing, we will take the chlorine, break the bond between the chlorine. This is simply bond enthalpy. Okay. Or you can say that it is what? It is enthalpy of atomization of chlorine, right? So this will give you half, you can write it in this way. So if you take the bond enthalpy of chlorine and divide by 2, that will give you the actual value. Now we'll convert this gaseous atom into electron containing chlorine, means negatively charged chlorine, I would say. And this is the electron gain enthalpy for this chlorine molecule, for this chlorine gaseous atom. So you got your Cl minus, you got your sodium. Now what you will do? You will add both of this. Okay, you will add both of this, and during this process, whatever the energy will be released or consumed, that is called as lattice energy. Clear? Okay. Now we will move to ionization in energy and electron gain enthalpy. So what is ionization? So first of all, you should be clear about the ionization equation. So ionization equation is basically, if you are taking a gaseous atom and you are abstracting one electron from it and getting Mg plus, M plus, then it is called as ionization enthalpy. Similarly, if you are adding one electron to the gaseous say atom, then we call it as electron gain enthalpy. Now we can write that at temperature T, if you have to write delta H reaction, then it is simply at temperature T, delta H is given as delta H at temperature 0 plus integration of Cp dt from 0 to T. Okay, so this is the formula for calculating delta H. Okay, clear? Okay, so what we have done here, say, so we have taken the delta H enthalpy at 0 degree temperature, and then we have added the Cp dt, which is simply Qp. Okay, which is simply Qp. The value of Cp for this species in above reaction is 5 by 2R. So for this M plus gaseous and M minus gaseous, it is 5 by 2R, because Cb is equals to 3 by 2R. So therefore we know Cp minus Cv is equals to R. That will give you 5 by 2R. Similarly, for ionization and for electron gain enthalpy, this value will be positive and negative. Okay, this will be positive and negative. Delta Cp will be positive and negative. Now we can write delta H ionization as E naught ionization plus 5 by 2 RT. Okay, and for electron gain enthalpy, minus of electron affinity, then minus what? Your electron gain. Okay, Cp. Clear? Next is enthalpy of solution. Okay, next is enthalpy of solution. So it is basically the enthalpy change when 1 mole of it is dissolved in a specified amount of solvent. So if you're taking a solute and 1 mole of it solute and dissolving it in a specified amount of solvent, then you call it as enthalpy of what? Enthalpy of solution. Clear? So the enthalpy of solution at infinite dilution is the enthalpy change when observed on dissolving substance in an infinite amount of solute, and when the interaction between the ions are negligible. So what I was saying here is that there is something called infinite dilution, in which we have also enthalpy of a solution. So for enthalpy of solution at infinite dilution, we take an infinite amount of solute. Means infinite means we will take such amount of solute so that the molecules cannot interact. So when an ionic compound dissolves in a solvent, the ions leave their order position as on the crystal lattice. They are now free in solution, but solvation of these ions also occur at the same time. This is shown diagrammatically for an ionic compound. Okay. So what are they saying is that there are two things when we dissolve a solid in a liquid. So first is the lattice enthalpy, that is to break the bond. between the atoms and take out the ions from it. Second is you have got your ions, but ions are what? They are charged. So second thing is you have to stabilize it, and that is done with the help of hydration. So delta H solution means dissolving a lattice, say lattice cubic into water dissolves two type of energy. First is lattice energy and second is hydration energy. So it is the summation of both of them. Therefore, solubility of most salt increases with rise of temperature because this enthalpy of solution is endothermic in nature. Clear? Okay. So why do fluorides tend to be less soluble than corresponding chlorides? Because fluorides makes the compound less ionic. This is the reason for that. Because of the polarization of the cations that is due to the fluorides. Next is enthalpy of dilution. So dilution means simply adding water. So when we are adding water to something, then that results in dilution. So suppose we are adding 10 molecules of water, okay, then that will result in HCO.10H2O and corresponding value is minus 69.01 kilojoule per mole. Okay, so it is known as the enthalpy of solution associated with addition of specified amount of solute to the specified amount of solvent at a constant temperature and pressure. So for convenience, we will use aqueous for water. So here actually you will see as dot 10H2O dot 6H2O. That thing is only written as dot 10 aqueous. So this is just a way of representing it. So we can have the following sets of enthalpy change, like if HCl is getting added with 25 equivalents of water, then it will give you minus 72.03 kilojoule of mole of energy for per mole. Similarly, if you are adding 40 aqueous solution of water or 40 molecules of water, then it will give you minus 72.79 kilojoule for per mole of HCl. Similarly, for third reaction, we have infinite aqueous solution added to the HCl. That will give you minus 74.85 kilojoule per mole. So it is simply enthalpy of dilution at infinite concentration. Okay, at infinite dilution. So if you want it for 15 aqueous, so what we are doing here, we are changing it from 25 to 40. So for that we have added and subtracted the equation accordingly. So it is heat withdrawn from the surrounding when additional solvent is added to the solution. Okay. So what are we diluting? We are already having 25 aqueous and we are still adding 15 aqueous. So it is basically the stability that is being provided, and enthalpy of dilution is dependent on the original concentration of solution and the amount of solvent added. Clear? Okay. Last thing, the values of del H shows general dependence of the enthalpy of solution and amount of solute. As more and more solvent is added, the enthalpy of solution approaches a limiting value. Okay, so at some time it will reach the value that is equal to infinite dilution. Okay, which is called as infinite dilution. So we have seen that if we subtract equations S1 from S2 in the above set equation, we obtain this. Clear? So this was for today's lecture. With this, I end my lecture. Thank you.